When we think about the scientific method, we often think about a very rigid process or a series of steps that you have to follow. And this makes sense because that's how it's often taught. If you are involved in a science fair or just do a specific project for a science class, you probably followed a really strict set of instructions. You had to write an introduction, you had to write a hypothesis, you had to design your experiment, and that was it. um, but really, when you're using the scientific method, it's really a thought process. And so when you think about a thought process, your mind bounces around. You think about things in different orders. You go, oh wait, I remember that. And so really, using the term scientific method makes it sound like a rigid process, like you're following a recipe, something that's inflexible. But actually, it's better to think of the scientific method as scientific thinking. Um, the only thing that really has to go in order is making an observation and asking a question. So initially, if you're quote unquote doing science or doing the scientific method, doing the scientific process, it always starts with an observation of some sort. And that observation piques your interest and makes you ask a specific question. After that, you might do a little bit of initial research. You might form a hypothesis, make a prediction, do an experiment, and then you might initially look at your results and say, ooh, that's not quite what I thought would happen, and then use that observation again to make another hypothesis. Or maybe you started out with two hypotheses and you want to test each one individually. So you don't necessarily have to do all of these things in the same order every time. It really is sort of a fluid process. And so if we think about it as thinking rather than a method, it really starts to make sense that that your experiment can change, that your predictions can change as you are going. The thing that is important here, though, is that there are a few components of each of these steps that need to be followed. So there are some specific criteria, say, for how you write your hypothesis or how you make a prediction, the types of things you do in your experiment to make them credible. And then there are specific ways that you interpret results so that people who are reading your work or seeing what you're doing know that they can trust that you're doing good work and that you're making an unbiased interpretation of your results. And that's what makes science trustworthy. And that's why people sometimes don't trust science, because some people allow biases to be introduced to their experiments. They tweak their conclusion a little bit to make their results fit the agenda of something else. But when you're doing science objectively, you should draw conclusions based solely on the results and interpretation of the data as you see it. So we're going to go through each of these parts, some in a little more detail than others. We're going to talk about this process, and we're going to talk about it in a straight line, in a step-by-step fashion, but just keep in mind that you actually can, it's a fluid process. It doesn't necessarily go in a straight line all the time. So one thing about scientific thinking is it's empirical. This means that it's based on experience and observations. And those experiences and observations need to be rational, testable, and repeatable. So we'll talk about a little bit later about some of the things that science doesn't test. But for now, we need to focus on what it does test. It does ask questions about things that are testable. If you can't design an experiment to answer your question, you can't get a good answer out of it. And so you need to ask a different question, design a different type of experiment, do something so that you are actually testing for the question and the hypothesis that you are asking. Another thing about scientific thinking is that it's self-correcting. So this means that you should be looking at the data and accepting when your hypothesis isn't correct. So if the process is working correctly and you see data that doesn't support your hypothesis, it doesn't mean that you're necessarily that your data is wrong. It probably means that your hypothesis was wrong. And so if you're doing this process correctly and you are going back to the beginning and saying, okay, that hypothesis was wrong, but I'm quite confident that my experiment was designed correctly, then you need to reevaluate. And that's why science is so fantastic, because it is self-correcting when it's done properly. So let's talk about some of the actual steps in this process. So I do want to note that these numbers deviate a little bit from our book. I'm actually following the steps in the process as they're listed in our lab manual. And that's because our lab manual breaks a couple of the steps down a little bit. So we're actually going to talk about the same things, they're just numbered slightly different. So if I say, discuss the 7 steps in the process, I'm talking about the ones from this lecture or from our lab, although all the information is actually contained in the book. So our first step is to make an observation. So we are going to follow an experiment in our book through this process. So one of the things that you might have heard is that certain supplements or vitamins will actually help reduce the length of the common cold. Vitamin C is one of them. My husband swears by vitamin C. I'll talk about that a little bit later. Another one is echinacea. So echinacea is an herbal supplement. And so we're going to follow this observation by some people that echinacea reduces the likeliness of catching a cold, or if you catch it, reduces the duration of the cold. So that's our initial observation. So scientific thinking begins by making an observation. Now remember, we have to, if we're going to do this process, we have to ask a question about this observation that's going to be testable. And so we're thinking about now things that we can test in some way. So usually these observations are observations of some sort of pattern or some sort of cause and effect relationship. So along the way over the years, people have taken echinacea for one reason or another, and they have observed that they think that it reduces the likelihood of catching a cold or the duration of the cold. So after we make our observation, we need to ask a question. And sometimes this kind of happens at the same time. You think, oh, echinacea seemed to have made my cold go away sooner. I wonder why. So there's your question. So there are different questions you can ask. One question is, or one type of question are causal questions. So most questions that you're going to answer with a hypothesis and with an experiment are going to be causal. So causal questions give you hypotheses about the reason behind some sort of observed phenomenon. So usually a causal question is going to be a why question. Why does this happen? So for example, you might be asking, why is my cold shorter? So your hypothesis would be that echinacea reduces the likelihood of catching a common cold. So the question that you're asking is actually a why question. Now this is compared to a descriptive question. These are not usually answered by hypotheses. And sometimes students get a little confused or unsure because you say, well, I can guess at the answer. And guessing at the answer is not really the same thing as a hypothesis, in the sense that a hypothesis as asking a why question, whereas sort of a guess at the answer is predicting a what question, if that makes sense. So a descriptive question is not one that's going to be answered by a hypothesis, and it's not that they're not interesting, but descriptive questions sort of explain or show the what. So for example, what is the range of a bald eagle? Well, a bald eagle might have a range of a couple thousand miles. It doesn't explain why they have that range. That would be a causal question. So if we're looking at echinacea reduces the likelihood of catching a common cold. Your causal question would be, why is my cold shorter? As opposed to a descriptive question that might say, how long was my cold? 3 days. You're not trying to explain anything, you're just trying to describe something. Another example of a causal question, why is it cold outside? The descriptive question would be, what temperature is it? So you might be able to predict the temperature. I'm recording this in winter. The average daily temperature has been about mid to high 40s. So I might predict that the outside temperature is 44 degrees. That's not the same thing as a hypothesis. A hypothesis would answer a causal question. So why is it cold outside? Well, now you're getting into a hypothesis about weather patterns and jet streams and things like that. Something to explain a phenomenon, why something is actually occurring. So the type of question that you ask is really important because that's going to affect whether or not you can make a hypothesis about it. Which leads us to step 3. So step 3 is formulating a hypothesis. Now you've probably done this before. I'm going to ask you to do it a very specific way, but we are always trying to answer that causal question. So a hypothesis is not a guess. Sometimes people will call a hypothesis an educated guess. And that's not exactly what a hypothesis is. A hypothesis is a proposed explanation based on initial observations. So if you're going to make a hypothesis, you do have to have a little bit of background as to what you are asking, as to what the question is that you're asking. So if we're talking about echinacea, you need to know a little bit about what echinacea is, what it does. You need to know why people are saying that they think it reduces the likelihood of the cold. You need to know a little bit about a cold. How long does it usually last? Are there other treatments that affect it? What causes it? Things like that. Because if you're going to make a hypothesis, you have to make a hypothesis that makes sense with the information you already have. It wouldn't make any sense to say, my hypothesis is that echinacea causes someone to never ever get a cold again in their lifetime. Because that's not what the initial observations are. The initial observations are that echinacea reduces the likelihood of a cold. So for a hypothesis to be useful, they have to establish an explanation for something, and they have to generate a testable prediction. So we'll get to predictions in a minute. Predictions are stating what you think the answer is going to be, what data you expect to get. So when we are doing a hypothesis, it has to be clear that if the proposed explanation is not being supported by evidence, a different hypothesis is probably the explanation. If you have designed a good experiment and your data doesn't support your hypothesis, it's basically science saying you need to change your mind. And that's one thing that science is really good for, is presenting evidence that tells people, look, this is the data, these are the facts, they've been tested in the right way, and our hypothesis has been shown to be false. And so that's a really important part of science. The other important part is that when we're looking at results, we have to accept that even if we are super passionate about our hypothesis, we might not support it. And so we are really evaluating the validity of the hypothesis, and we have to keep bias of interpretation out of it. That's what makes science strong. So there are a couple of different ways you can write a hypothesis, and it really depends on what you're going to use it for. So you can write what we call a null hypothesis, which is basically just a negative statement. So null means nothing or negative. So a null hypothesis says that there's no relationship between the two factors. So our null hypothesis for the echinacea experiment might be echinacea has no effect on the likelihood of catching a cold or the duration of cold symptoms. So this is a hypothesis that states a lack of relationship. We can also write the alternative hypothesis. And the alternative hypothesis is going to suggest that there is a relationship. Each of these is equally valid, but the negative statement is usually easier to disprove. If you're observing something, it probably means there is a relationship of some sort, and so the null hypothesis to say there's no relationship is usually a little bit easier to disprove. The alternative hypothesis is sometimes harder to disprove just because it is harder to definitively say this is the only cause. So related to that, when we are interpreting hypotheses, we do not ever prove a hypothesis. We can never say that this is absolutely and permanently true in every situation. And that's another thing that people sometimes incorrectly use the scientific process before. Oh, I proved that echinacea shortens the duration of the cold. Well, now you're like, yes, this is fantastic. I'm going to put all my money in echinacea. And then you take it and it doesn't do anything. So science does not prove, it supports. And that is one thing that I promise to ding you on your lab reports. If you tell me that you have just proved something, I'm going to say, no, you didn't. You supported it. Okay. So science is not proving things, it's supporting things. And the important thing about science is that we disprove things all the time, even things that we previously thought were quote unquote proven. And so this is also important for you if you're looking at advertising and things like that, and proven to reduce the length of a cold, or similar things like that. These claims are used in advertising, and they're used because people trust science, and they're basically using that idea. All right, so let's look at these two hypotheses. So I actually have these in backwards order from the previous slide. I'm sorry about that. So if we're going to look at our alternative hypothesis, so if we're thinking about the echinacea experiment, our question is, why is the duration of my cold been reduced, or why is my cold less severe, whichever question you want to ask. So our hypothesis would be echinacea reduces the duration and severity of the symptoms. So we're showing a relationship between echinacea and the cold. If we want to write the null hypothesis, echinacea has no effect on the duration and severity of symptoms. So there's a very subtle difference between those. And no matter which one you choose, you can use the same experiment to support or not support these two. It doesn't actually matter too much because you can use the same experiment. It just really depends on what you want to show. Do you want to show that echinacea reduces the duration, or do you want to show that it doesn't? It's kind of up to you. And there are certain times when we actually use the null hypothesis in science, like when we're doing different types of statistical testing and things like that. Sometimes we'll use the null hypothesis. So let's develop this hypothesis. So your hypothesis needs to very specifically address the question that you are asking. And so we want our our treatment that we're going to be giving our test groups to be stated, and we want to state what exactly is going to happen. So we are proposing that echinacea reduces the likelihood of the cold or reduces the duration. I would personally suggest keeping these as simple as possible. So our book uses this reduces the likelihood of catching and the duration. I tell my students, they just pick one. I would personally have chosen echinacea reduces the duration of cold symptoms. But it is what it is. Our book has chosen a slightly more complicated experiment, and that's okay. So this is our hypothesis, and they have developed this really elegant experiment to test whether or not this hypothesis is correct. So we're going to come back to how they actually designed this experiment in just a few minutes. So I am actually skipping around a little bit in our textbook. But there are hypotheses in biology, and then there are science, and then there are theories. And they are related, but very different things. So a hypothesis is a proposed explanation for something. It usually answers a specific question. It's very direct and narrowly focused. And a hypothesis is what you're going to be testing. So they're usually small. We're looking at the effect of one thing on one other specific thing. They are generally very isolated questions. But we also have these theories. So kind of like hypotheses, when I said that people sometimes think of them as an educated guess or just a sort of a random fact about something. A theory is not just a speculation or a guess. So in everyday language, you might say, oh, I have a theory about that. And really, you're just rambling about something that you have an idea about. And I'm not saying that rambling about things and having ideas about things is bad. I'm absolutely not. But when we're talking about a scientific theory, they are not speculation or guesses. They are hypotheses that have basically stood the test of time. They are hypotheses that have been repeatedly tested. They've been supported by a large body of evidence. And they are hypotheses that explain a wide range of related questions. So a theory is so well supported that it's unlikely to be altered by new evidence. So it can sort of be thought of as a biological fact, repeatedly tested and supported. That does not mean that it could never be disproven. Remember that I said that a hypothesis is never proven. It's the same thing with a theory. You can support it and support it and support it. And it gives it greater credibility, but that doesn't mean that it is true in all cases every time. And therefore we are not proving, we are simply supporting. On the flip side of that, we can disprove them. So some new evidence, some new way of evaluating something might come along that we don't have right now and make us reevaluate those theories. So we're going to take a quick look at an example of a theory that our book doesn't really go into later. There are a couple of other theories we will get into. We'll get into cell theory next chapter, which is basically the theory that explains that where cells come from, where life comes from. And then in this class, we will also talk about the theory of evolution. So both of those theories are very widely supported by a lot of different things. But I wanted to give you another example, something here to demonstrate the difference between a theory and a hypothesis. So we are going to talk about the germ theory. So the germ theory states that there are several tenets to it. One is that microorganisms or germs lead to disease. Now you probably sort of already know this. You know, people say, wash your hands during cold season, wash your hands before you eat, things like that. But Prior to the mid 1800s, people didn't really know this. They didn't really know where illnesses came from, and they sort of thought that they floated through the air as like poisonous gases or something. Um, so this idea that disease was actually caused by something that you couldn't see was, a little unsettling and earth-shattering to some people. So microorganisms cause disease. These organisms are too small to see without magnification, and they invade humans, animals, and other hosts. So that's kind of a scary thought. I think even still today, it's a bit scary, probably less scary than it was, 200 years ago. When people didn't know these things even exist, they had never seen them before. Whereas, because of all of our scientific equipment and knowledge now, these germs are pretty much common knowledge. But at the time, it was proposed that these were just little tiny organisms that we couldn't see. And then these organisms grow and reproduce in their hosts, and that's what causes disease. So there were several people along the way that sort of were proposing and studying these things, but the general public didn't know this. So I'm going to talk about a couple of people that did experiments to support this initial hypothesis that germs lead to disease and that they're too small to see. So we're going to talk about Louis Pasteur real quickly, Joseph Lister, Robert Koch. I'm not going to go into a lot of detail with these guys, but I just want to demonstrate that there are different ways you can support the same theory to sort of round it out and make it this sort of broadly supported, widely accepted idea. So Louis Pasteur, you are probably familiar with the term pasteurization. It's this process of heating a food. It was initially used for wine and milk. Heating food high enough so that it kills bacteria that might live in it without curdling the milk or turning the wine. So that was originally not a thing. So Louis Pasteur did a lot of things. I wrote a paper in grad school on him that was ridiculously long. I know more about Louis Pasteur than I ever cared to know about Louis Pasteur, but the thing that he did that we are most grateful for was basically showing that you have to have life in order to get new life. Now, the exception to this is the beginning of life, course, because there was no life and then there was life. But aside from the very first cells, you have to have cells to make more. And that's part of the cell theory, but it's also related to the germ theory. So he had this really elegantly designed experiment, and he had these really cool gooseneck flasks, and these were important because you couldn't really get anything backwards into it. So you couldn't get anything from this end here all the way down into this bubbling liquid here. And so he did 3 different things. He applied heat, and we all know now that heat kills living things. So he basically sterilized this liquid. He let it sit. And he let it sit, and it remained sterile because nothing was going to travel back through this gooseneck flask. So then he did something different. He applied heat. Then he broke the neck off. Well, we all know that if you leave something uncovered in the refrigerator or on the counter, eventually things are going to grow in it. And that's exactly what he saw. When he broke this flask, when living organisms could now get into it, when things floating in the air could get into it, bacteria grew. So then he did a 3rd experiment. He applied heat to the same gooseneck flask. This time he used one that wasn't broken, and he tipped it over a little bit and allowed it to sit. So at this point, now bacteria only have to get in this little bit before they enter. And so then he found that bacteria was present. So he was able to show that if you start with no life and there's no source of life, you don't get life. But if you start with no life and there's a way for life to get in, you now have life. So this suggested that bacteria could get into certain places under certain conditions when there was seemingly no way for them to get in, or when there was initially no life present. I'll talk about Joseph Lister a little bit less. Joseph Lister was a British medical doctor, and he was he realized that in certain medical wards, I believe he was working at a male-only surgical ward in England, he found that when he cleaned his medical supplies, people didn't die. So we take for granted this sort of sterile environment, and we're completely shocked if anyone ever gets sick from being in the hospital, because they shouldn't, because everything should be clean and pristine. But it actually wasn't. Before Joseph Lister, people were using all kinds of rusty, bloodstained nastiness, and people were dying. And when he started sterilizing his medical equipment and his surgical equipment, washing hands, people started living. And so this supported the germ theory that even though you couldn't see that there were bacteria and things growing on all of these instruments, that they actually were there and they were being transferred to patients. So that was a huge, important piece of the medical field. So Robert Koch was also important because he identified the causes of tuberculosis and anthrax. So he actually was able to isolate the germs that were causing these illnesses. And that was really important because before him, nobody had actually been able to say this bacteria causes this illness. So if we look at all three of these individuals, we show that life doesn't come from nothing. So if you suddenly have an infection of some sort, it is because something has infected you. You didn't breathe bad air necessarily, although obviously things do travel through the air, but illnesses were not just sort of caught because a bad wind blew by. And then of course that you can transfer these organisms, and these organisms can infect and things. So this germ theory is very widely supported, and it's important in our lives today. It governs how we clean things, how we wash our hands, how we take care of ourselves, how we practice medicine. And so it's really important. So I've talked a lot about hypotheses and theories. Let's go back to our process here. Oops, I'm sorry. So I'm going to talk about the next couple of steps sort of together. Step 4 is to design a test. So I'm actually going to come back to this after I talk about the prediction, just because I find it easier to talk about the prediction and then talk about the test. But our lab goes through step 4 and then 5, which is the prediction. So we're going to design a test, and we're going to come back to talking about the things that you have to do to make sure that your test is valid, basically. But I'm going to skip to forming a prediction. So your hypothesis and your prediction sort of go together. So basically, you're going to make a hypothesis, which is the explanation to your question, your causal question. Why is this happening? Well, this is why it's happening. So after that, you'll design your test to test your hypothesis, and then you're going to predict the outcome. If my hypothesis is true, then I expect these results. So if your hypothesis is not true, you won't get those results. So these are written as an if-then statement. And this is another subject that students get a little confused on, because they like to break up their hypothesis into two pieces and make it a prediction. And that's not actually what you're doing with the prediction. You're saying, if my entire hypothesis, then these specific results. So your hypothesis should never say specific results. So we've been looking at this hypothesis: if echinacea reduces the likelihood of catching the common cold. So we've said reduces, but that's not really any data. We've not given any explicit data. So our hypothesis: if echinacea reduces the likelihood of catching the common cold, then individuals that take echinacea have a lower chance, and the duration is shorter. So you can see there now we're starting to get into measurements. Lower chance, shorter duration. So those are measurable data. So our whole prediction would be something like, if echinacea reduces the likelihood of catching the common cold and the duration of the symptoms of the cold, then, now's our prediction part, individuals taking echinacea should get a cold less frequently, and when they do get sick, their illness should not last as long. So now we are introducing some measurement. So the hypothesis is the explanation. The prediction is the data you expect to get to support that hypothesis. So these will become clearer when we start practicing them and when we start doing them. They probably are already a little bit clearer from your lab on Monday when we've actually done this. So another example might be, why is my best friend shorter than me? My hypothesis might be she drank a lot of coffee and coffee stunts your growth. So let's write a prediction. If coffee stunts an individual's growth, then my predicted data, average height of coffee drinkers should be lower than the average height of non-coffee drinkers. So we've got my prediction that my best friend is short because she drinks too much coffee. My hypothesis that she's short because she drinks too much coffee, and my prediction that if this is true, people who drink coffee will be shorter than those who don't. So as I said, we'll continue to do some examples of these throughout the semester.